continuation of our lecture on relation analysis. Today we will be studying regression analysis. Regression analysis we have already done one lecture, and regression analysis we will be doing a couple of more lectures as well. So, in today's lecture we will basically learn simple linear regression. Simple linear regression, as I already mentioned in my last lecture, it is like when there is one independent variable and one dependent variable. That means the dependent variable we call it the response, independent variable we call it the regressor. So, when the one in the dependent variable, when the response is dependent on the basically the regressor, and they are basically linearly related, and we can find a function that the relation basically if we want to find out the how these two variables are related, this independent variable and the dependent variable, how they are related. If you can find the function to it, a linear function basically if it graphs a straight line. So, those will be discussed in details, and that is in simple linear regression we will be discussing those. And now the function that we will find out for simple linear regression, which will give an independent variable to find out the value of the dependent variable, the function that will do that. So, now this function, how good this function is, how is this function is properly fitting the relations. Now that will there are different ways to check that way. So, now one such measure is called quality of fit. So, we will be discussing one such measure of finding out the how good our function is, the function that we have found out for the simple linear regression. This too we will be discussing in this lecture. So, now coming to regression analysis. Well, as I have already mentioned in my last class, there's relation analysis. There are basically two types: regression analysis and logistic regression. Okay, well, I have remember in one of my lecture I told you relation analysis, there are basically two categories. One is correlation analysis and another is regression analysis. So, here basically I can put one more thing. This is correlation analysis. Okay. Correlation analysis, regression analysis and logistic regression. So, correlation analysis is we have discussed, I am just leaving that for the time being. So, now coming to this regression analysis. So, will be in the regression analysis, again there are three different types of regression analysis, that is linear regression, non-linear regression and auto regression analysis. So, we will be discussing this three regression analysis in three different lectures. And again coming to linear regression and non-linear regressions, there are again simple linear regression and multiple linear regression. Similarly, for non-linear also simple non-linear and multiple non-linear. So, simple means when the independent variable is just one independent variable, that is just one factor, and when I tell it is there are in many cases there are more than one factor. Then one good example is remember when I have given an example, price of a house in a particular locality of the same size, square feet area. So, we know the price of a house in a particular area as per the square foot area. So, that is one factor. One area is that's a square foot area, that is the one variable, and again the price of the house may vary based on the age of the house as well. Okay, isn't it? It can vary based on the square feet area as well as it can vary based on the age also. So, there are two factors. When there are two factors are involved, when there are more than one factors involved, then we call, if it is a linear regression, then we call it a multiple linear regression. If it is non-linear, then we call it a multiple non-linear regressions. So, in this lecture basically we will be discussing simple linear regression, that is one dependent variable, one independent variable. So, let us see the example. It is a very simple example. Here there are basically two variables, one is the hours of study and another is the exam score. So, this is hours of study and the exam score. Now, here can you tell me which is the dependent variable, which is the independent variable? Definitely hours of study cannot be a dependent variable. Hours of study does not depend on the exam score. Basically, exam score may depend on the hours of study. So, here my independent variable is the hours of study, that is my regressor. Independent variable is also called a regressor. So, my hours of study is the regressors and exam score is the response or the dependent variable. So, here this data is given basically for how many students, say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, for 10 students, the hours of the hours they put into studies, and consequently the score they get in an exam. Okay. So, I want to find out, is exam score anyhow related to the hours of study? Is there any relations between the exam score and hours of study? So, if I just want to find out, is there any relation between exam score and hours of study? If I just want to find that, is there any relations, then what I'll do? Then I'll go to correlation analysis, right? So, and basically correlation analysis will give me, is there any relation, plus as well, if there is relation, what is the strength of the relation as well. So, now here that is not my objective. Here my objective is that, of course, it has to be related. Once it is related, then only we can go to the next part, right? Now, my next part is that if I want to find out, if I put in say 4 hours of study, what will be my likely exam score? Okay, if I put in my 4 hours of study, what will be my likely exam score? So, if I want to answer such type of question, definitely it's not a question of correlation analysis, it's a question of regression. So, first what I did is I just try to plot the data. It's just simple, it's a scatter plot, and I just try to draw a straight line, just what to say, so that a straight line which, so that more maximum of the points falls in the straight line. If not, if the points does not fall in the straight line, as it as at least it moves near by the points what is given. So, from this you can see, yeah, it has a linear sort of relationship. So, now from that I'll now try to find out what is there any relationship, what is the relationship between this x and y, that is the hours of study and the exam score. Now, first let us define regression analysis formally. So, what is this? A regression analysis is a statistical model to deal with the formulation of the mathematical model. Okay, it is a statistical model. What is this? It formulates a mathematical model. What mathematical model? Depicting relationship amongst variables. It gives a mathematical models which depicts the relationship among variables. What variables? Independent variable and dependent variable, which can be used for the purpose of prediction of the values of the dependent variable given the values of independent variable. So, this is regression analysis is a mathematical model which depict relationship between two variables, that is dependent and independent variables, and it is used for the purpose of predicting the value of the dependent variable given the values of the independent variable. So, given the values of the independent variable in the just last example what I have seen, given the value, suppose my hours of study I have put is 4 hours, then what may be my likely exam score? So, I am trying to predict on the dependent variable is the exam score. So, I basically need a mathematical model which gives the relationship between these two. The model is nothing, it's nothing but just that y is equals to fx. What do I mean by model? Model is nothing but just y is equals to fx. So, my x is the independent variable, y is the response variable, dependent variable. So, I just need this function. What is this function? How y is related to x. Okay. So, here is just a picture how the different regression models look like. If it is simple linear regressions, then it will just graph a straight line, maybe in the form of y is equals to mx plus c or y is equals to alpha plus beta x. So, where if I write y is equals to, this is very irritating. So, y is equals to alpha plus beta x if I write. So, alpha is the intercept, beta is the slope. Okay. Slope of the straight line, alpha is the intercept. It basically at what rate it moves corresponding to x, how y moves corresponding to x, that gives the slope beta. So, that is a linear regression model. Now, if it is if there are more than one factor, as I have given the example, if the property is not only dependent on the square root, it also depends on the age. So, more than one factor, then if it is more than one factor, again it may be linear or non-linear. If it is a linear and more than one factor, then what happens? Then again we may graph a straight line, but it will be in a multi-dimensional plane. So, here you see there is a multiple linear regression. So, and if it is a non-linear regression, it will graph a curved sort of pattern. Okay. So, this is an example of figure for non-linear regression. So, coming to simple linear regression, we have, as I already mentioned, we have two variables. One is called the response or the independent variable, other is the response or the dependent variable, and other is called the regressor or the independent variable. This is easy to remember. Response is the output, right? So what is the output? Output is basically we are doing something to get the output. So output will be definitely the dependent variable. So that is the response. One is response, other is the regressor. Okay. So a reasonable form of relationship between response y and regressor x is a linear relationship, that is a form of y is equals to alpha plus beta x, where alpha is the intercept, beta is the slope. Okay. So now this alpha is equals y is equals to alpha plus beta x, that is a mathematical model that we have considered. But then based on the points, what we, if you just plot the points, whatever data we have, based on the data we have plotted the point, and we have tried to find out the line that crosses through these points. But you may see there may be infinite lines that may cross through this point, because it is not, it is very rarely that is the case that all the points will fall on a straight line that we have made, that we have modeled. So, so when that is not the case, there may be infinite lines that will cross through these points. Okay, so when we have infinite lines, means there will be different values of alpha, there will be different values of beta s. So now the concept of regression analysis, what it does is it deals with finding the best relationship between y and x. There are infinite lines, we have to find out the best line that connects y and x, that gives the relationship between y and x, and hence the best fitted value of alpha and beta. Baseline means the best fitted value of alpha and beta, and that also quantifies the strength of that relationship. So that is the main objective of the regression analysis. You have to find out the best relationship, okay, between this y and x. That means we have to find out the value of the alpha and beta, that is the parameters. Alpha and beta are the parameters. Okay. So now actually here there is one thing, like if I just write y is equals to alpha plus beta x, that means if I know alpha, if I know beta, that means given x I can find y. So that means it is a deterministic equation. So for given any value of x, I will be able to find out the value of y if alpha and beta is known. Now see the example, like in the first class when I was talking about regression analysis, I have given few examples, like if I the amount of money spent on the promotion of a movie depends, that will help me in predicting the box office performance. If I spend more on the more money on the promotion, that my box office performance will be more. Means I will be able to predict based on the amount of money which I spend in the promotion. But sometimes we see if many movies where we have spent a lot of money on the promotion, but still it tanks in the box office, right? Same is the case to the advertisement. Sometimes we based on the usually based on the advertisement expense, we can predict the revenue of an item. But sometimes though the advertisement is, we have spent quite a lot on advertisement, but still the revenue is not less, still the product could not be sold. Again, the another one example what I have given is the engine volume. Different automobile engine volume is same, but then the mileage is different. Again, this this price of the house in the same locality, same square feet, but still some houses are sold at a higher price, some houses are sold at a lower price. So you see that this is not a deterministic equation. This is what? This is a deterministic equation. So basically from this example what I have just told, and there are many such scientific example, engineering applications, where we will see that this relationship, it is not a deterministic relationship. There is another some random component to it. That random component I am calling it as epsilon, that is the error. This random component, basically this random component, the engineers or the statistician who calculate this, either they don't know what this random component is, why the price of home in the same locality with the same square foot, why it is different, this random component, this random portion, why it is so, either they don't know or they don't use it for calculation. There might be some other factors which are beyond their control, so they don't use it for their calculation. So there is a random component. Similarly for all the other examples. So this random component makes the regression line random. It is not a deterministic line. So we have so our basically the regression line is this: y is equals to alpha plus beta x plus epsilon. Okay. So Now here x is very much a deterministic value. X, we just take it, the value which we calculate, which is already given to us, like the number of hours which I will put in study, that is 4 hours. There is no randomness to it, that is a deterministic value. So just there may be in measurement, there may be some negligible error in measurement. Other than that, there is no indeterministic part to it, no randomness to it. But for the independent and dependent variable, there is a random component attached to it, which makes because of which the equations that maps the dependent variable to the independent variable is no longer a deterministic equations because of this epsilon. Okay. Now here this epsilon is a random variable where expected value is equals to 0. This is the assumption we take. For a linear regression to be valid, our epsilon should be, our error component, this error should be such that this mean of this error should be 0. If the mean of this error is not 0, basically the model which you come out, that model is not a proper model actually. So, we have assumed that the mean of this expected value of epsilon is 0 and its variance, it has a constant variance, homogeneous variance, that is equals to sigma square, a constant variance among all the epsilons, among all the errors. Error means the difference of the point from the straight line, from the line which you have got, the regression line. The quantity sigma square is often called the error variance. Okay. Now, what does this expected value of epsilon is equals to 0, what does it implies actually? This implies that x and y are distributed around the true regression line. Okay. This, what does the expected value of epsilon is equals to 0, but we have assumed that here epsilon is a random variable with expected value of epsilon is equals to 0. So, what does this imply? This implies that at a specific x, the y values, for a specific x, the y values are distributed around the true regression line. Okay. True regression line, this is y is equals to alpha plus beta x, and that is the positive and negative errors around the true line is reasonable. What does this expected value of epsilon is equals to 0? It implies that for a specific x, my y values which are distributed around the regression line, it will be above the regression line or down the regression line, it will be distributed around the true regression line in such a way, that means the positive errors means if it is above, negative error means it is down. If the positive errors and the negative error around the true line is reasonable, it is not very high. Okay. And when it is reasonable, then we can assume that E of epsilon is equals to 0, and that is a necessary condition actually. If we don't assume that expected value of epsilon is equals to 0, then that means our fit is not proper, that means our regression line, the model which have come up is not proper line. So, because there are lots of error to it. Okay. So, now the next what we need to do is that, okay, we found that. So, we will basically there, as we know, there may be infinite lines. So, we have to find out the best line that fits the data points, that crosses the data points in such a way that expected value of the random component, that is expected value of epsilon is equals to 0. And once we find this line, so basically now the next step will be, we have to find out the coefficient. Finding the line means until and unless we know the coefficient, that is the alpha and beta, the line is not complete, our mathematical model is not complete, right. So, now our next step, the values of the regression alpha and beta are to be estimated. So, value of alpha and beta are not given to us, we will have to estimate this value of alpha and beta from the data. Okay. So, now suppose, so what we'll do, we have say we have drawn an arbitrary line. Okay, now this the line is y is equals to alpha plus beta x. Now that means we have to find out, until and unless this line carries no meaning, until and unless we know the value of alpha and beta. So basically we have to estimate the value of alpha and beta. So suppose we denote the estimate for alpha is equals to a and for beta is equals to b. Suppose we have we got an estimate. Suppose we take alpha is equals to a and beta is equals to b. Suppose this is the estimate we got. Okay. So if this is the case, then what is our line now? Our line is now a plus bx. A plus bx. Now for that, instead of y, I am writing is y cap. because this is my assumption. I have assumed that value of alpha is A, value of beta is equal to B. With this assumption, the line I got A plus beta is A plus Bx. Suppose I got is y cap. I am using a different variable, no? That is y cap, where y cap is the predicted or fitted value. Okay, suppose this is my actual line. This is my actual line. Y is equals to alpha plus beta x. I don't know what is alpha, what is beta. I don't know. There is in the space there is a line. Basically, there is a line. That line is y plus beta x. Y is equals to alpha plus beta x. That is my actual line. I don't know. I have estimated the value. Say I have estimated the value of alpha is A and estimated the value of beta is B. And with that, I got a line that is A plus Bx. So suppose that is my the A plus Bx gives the value y cap. This is my predicted fitted value. Okay. So now we need to find out. We have estimated that value A and B. Okay. Estimated that A alpha is equals to A, beta is equal to B. We have to find out what is that A, what is that B. For that, first we'll have to know the term. There is a term called residual. So what is this residual? So basically, the thing is that to find out the values of alpha and beta, one of the most used method is called the least square method. So we will be learning this least square methods to estimate alpha and beta. So in this least square method uses a concept called residual. What is residual now? A residual is essentially an error in the fit of the model. My predicted line is this, isn't it? What is my actual line? Actual line is equals to y is equals to alpha plus beta x. Okay. So from these two lines I get a residual. What is that? Thus the ith residual is E of I is y of I minus y of I cap. That means the difference between these two. This is my actual line, this is my predicted line. So residual is difference between these two. This portion, this is my residual. So E of I. So when I can say that the value what I have predicted is a good fit. Okay. So when my E of I is as small as possible, isn't it? So my residual, both negative residual and positive residual, when it is as small as possible, then I can say that it is a good fit. Okay. So my residual should be small, as small as possible. Now this is, I have found out EI just for one value of xi. Similarly, I will take different values of xi, x1, x2, x3. Here, like for the example, I have taken different hours of study 1, 2, 3, 5, 7, 9, and I took different xi's. For different xi's, I got yi value, isn't it? So similarly, I will find out the residual for all such xi's. So this is then to to find out so what is the best? I told you the best is when this residual is as small as possible. So what will I do is that now this residual can be positive also as well as it can be negative also. So I will take the square. This method is called the sum of squares error. So what will I do is that this is the residual sum of square is often called the sum of squares of the errors about the fitted line and is denoted as SSE. So sum of squares of the errors. Okay. So it is called sum of squares error, SSE. So how it is? SSE is nothing but summation of all EI squares. What is EI? EI is yi minus yi cap, actual value minus predicted value. So similarly for each xi, I will get actual value and predicted value. So SSE is summation of all such yi squares. So this is EI square is nothing but this is the thing. And what is yi cap? Yi cap is A minus B xi. Isn't it? That's what we have predicted the value. We have predicted the value of alpha and beta. We got this. So this is my SSE is this. Okay. So I need my SSE to be minimum. So under what situation my SSE will be minimum? For what value of x, my x and y, my SSE will be minimum. So to find that out, we need to minimize the value of SSE and hence to determine the parameters of A and B. So under what situation this SSE will be minimum? For what value of A and for what value for this different? Because A and B, these are the parameters which I have assumed. So for assuming this A and B, I have got a predicted value. So now this difference of predicted and original actual value is my EI. So sum of all this EI, that I am calling it SSE. Now I need to minimize this SSE. So And so, and for what value of my parameter estimation, because of this different parameter estimation only I am getting a different line, isn't it? So, for what value of these parameters A and B, I will get a minimum SSE. So, how to do when I want to find a value of the variable so that the function is a minimum. So, it is just partial differentiation and then we equalize it to 0, right. So, differentiating SSE with respect to A and B. This is a simple function concept all of you know. So, I will do partial differentiation SSE with respect to A, then I will do differentiation of SSE with respect to B. When I differentiate SSE with respect to A, I got this, and with respect to B, I got this. Now, this I'll equate it to 0, this I'll equate it to 0. I got two equations. From these two equations, I can find out the value of value of A and B. I want to find out the value of my parameters A and B, isn't it? So, that's all, equating the partial derivatives to 0. So, I got these two expressions. Simple, this simple, nothing to explain here. All of you know how to find out the minimum of a function, under what value the function will have a minimum value. That's all, nothing else. So, these are the two expressions. So, once we solve this equation, this is my value of B, this is my value of B, and this is my value of A. By solving this two equation, I got my value of A and B. So, this is the least square method to estimate alpha and beta. This method is called least square method to estimate the alpha and beta. So, what alpha value I have estimated as A and beta value I have estimated as B. What is my A value? This is my A value, this is my B value. So, A value and B value all I am getting it in terms of xi's. See, xi's and yi's basically. So, this is my B value, I got all my terms in xi, yi, x bar, y bar all from the data itself. I have a set of data, right. Similarly, I got the A value also. So, now from this, okay, we found out the value of the parameters A and B. So, I got the line A is equals to y is equals to A plus bx. That is my line which feeds the which basically gives the relationship between x and y. Given a value of x, I can be able to predict the value of y using this line y is equals to A plus bx. I got the line. Now, the question is that is this line properly fit? This line properly fits the data that is actually given, or this line maybe it is not a proper fit. So, for that we need to find out one measure that is called measure of quality of fit. Okay. So, the one measure of quality of fit is this R square measure. It is a very commonly used R square measure to find out the quality of the fit of the regression line, quality of the fit of the mathematical model that we got. So, this is nothing but a mathematical model, isn't it? Y is equals to A plus bx. So, how good the line is? So, this quantity R square is called coefficient of determination. This is used to measure the proportion of variability of the fitted model. The fitted model that I have fitted, that means the straight line that I have fitted is how much variability is there from the actual. Means actual, if I actual value which I have from xi and yi, what value it gives, and what value this line gives, how much variability is there. So, basically that is the quantity R square. The quantity R square is the coefficient of determination is used to measure the proportion of variability of the fitted model. So, R square, to define R square basically we need two terms. One is SSE, that is what to say, that we have just already seen some of this. This one, this SSE. What is this SSE? Sum of squares error. How did you find out the sum of squares error between the what the predicted value and the actual value? So, for R square calculation we need two values. One is SSE and another is SST. So, this is SSE. SSE is nothing. It signifies the variability due to error. SSE, what does it signify? This is the formula for SSE. We have just now seen, isn't it? What is variability due to the error? Means the it is basically how much is the error between the predicted line and the actual line. So, that is my sum of squares due to error. And another one term that we knew is total corrected sum of squares. Total corrected sum of squares, you are not new to this term. We have used this term while learning ANOVA, remember. So, total corrected sum of squares, it is basically again it is also variability of the data from the mean of the data. Okay. So, what the data that we have used for a regression analysis, that all the data that we have used for regression analysis, how much this data is variable from the mean of that data. Okay. See, SST is nothing but yi minus y bar. This y we have taken some data xi and yi, isn't it? So we have taken some data xi and yi. This yi's that we have already, some data we have based on this data only we are finding a model. Without the data we cannot find a model, right? So now this data, how much this data there is variability in this data, variability in this response data. So that is SST. Okay. Now, so what does R square? See, SST represents the variation in the response values. How much this response, yi are the response values, how much variation is there in the response value. That has nothing to do with the error or something like that. We have taken different x value, for different x value what is the y value. So that is this y, different y values that we get, this what is the variability of this data, that is the SST, total sum of square, total corrected sum of squares. So my R square is nothing but 1 minus SSE by SST. Okay, 1 minus SSE by SST. Now, if my SSE is equals to 0, suppose, under what situation my SSE will be 0? If my SSE is 0, that means my line is a very good fit, isn't it? My line is a very good fit, then only my sum of squares due to errors is equals to 0. In that case, what I will get, R square is equals to 1. That means it is a very good fit, quality of fit is very good. Okay, even if suppose my SSE is quite less than SST. If it is quite less than SST, it is not 0, but quite less than SST, then also I will get a very very less term here by if I divide this SSE by SST, and my R square will be closer to 1. That also indicates a good fit. Of course, 1 is a very good fit, and values which are closer to 1 also a good fit. Now, if SSE is almost equal to SST, that means the sum of variability due to error as well as the variation in the response, variability due to error is so high that we are getting almost equal to the variation in the response value. Variation in the response value is different thing, isn't it? My variability due to error is so high that I am getting, it is almost equal to SST. Then what will happen? My R square will be equal to 0. That means my fit is not at all a proper fit. It is not a good fit. R square is equal to 0 means it is not a good fit at all. Okay, and theoretically, in fact, my R square value can be less than 1 also. Under what situation my R square value will be less than 1? When my SSE value is bigger than SST. See, pay attention please. When my SSE value is bigger than SST, sum of squares due to error is bigger than SST. You can imagine. That means what the fit that the line I have got, that is not at all it is showing totally a wrong trend. That is not at all the line that actually the that these two variables, independent variables and dependent variables are fitted. That the line, that the regression line I have got, that is totally in the opposite trend. It is not showing the proper trend. That's why I am getting the error, such a high error that it is bigger than SST. So theoretically, R square less than 0 is also possible. Negative R square is also possible. In that case, it indicates my quality of fit is. Question of quality of fit doesn't come basically. It is totally as the fit that regression line that I got, it is totally showing a wrong trend. Okay. So, see, if the fit is perfect, all residuals are 0 and R square is equals to 1, as I told you. SSE is equals to 0, then all fit is perfect, all residuals are 0. That is, of course, it is very impractical, but getting a value which is closer to 1 is also very good fit. So, if SSE is only slightly smaller than SST, then R square is equals to 0, almost equals to 0, that is a very poor fit. So, you see this is a very good fit, almost all the points are in the line or very near the line, and this is an example where it is a very poor fit. Okay. So, in this lecture we learned the basic methodology of simple linear regressions. Okay, what that includes? That includes the formulation of the model, how we basically formulate the model to get the function between the dependent variable and the independent variable. Then we have seen what the least square method, that approach to solve the model parameters, that is alpha and beta, that is the intercept and the slope. And also we have seen the coefficient of determination measure to measure the quality of fit. Coefficient of determination, that is the R square, to measure the quality of fit. So we have discussed all these 3 things in this lecture, and so this is the reference, and thank you guys.